In this video, we are going to solve problem 4-107 that is taken from chapter number 4, Pure Bending, and book name is Mechanics of Material by Beer and Johnston, 6th edition. So statement is the four forces shown are applied to rigid plate supported by a solid steel post of radius A, knowing that P is 100 kilonewton and A, which is radius of the steel post, is 40 millimeter. Determine the maximum stress in the post when the force at D is removed, and in B when the force at C and D are removed. So you can see these are the four forces that are acting on a rigid plate. This is the plate, and this plate is supported by this solid steel post, and it's having radius. You can see the radius is given as A. This is the post portion. Clear? So the load P is 100 kilonewton and radius is 40 millimeters. So you have to find the maximum stress in first part when this D force is removed, and in second part when you do not have C and D forces at this point. So let's start with the solution. What we will do is that first we will find the stress for a solid circular post. For that I will write for solid circular post or section of radius A. We know that area will be equal to pi r square since radius is A, so we can write it as pi A square. And what will be the moment of inertia? We will use it later on. So moment of inertia is equal to pi by 4 r square, and that is r4, and r is A. So pi by 4 A power 4. Now what we will do is that we will find the normal stress and this at this condition, normal stress at this condition. And you can see you have four axial loads. These are the axial load. These are not centric load. So these are axial load. And if you want to apply this axial load into centric load, so what we will do is that we can replace this total force will be equal to 4 times P, and you can see that this is your Z axis, this is your X axis. So first we will take the moment about Z axis. So moment about Z axis will be this one. You can see that this is Z axis. So this force P into perpendicular distance A is producing clockwise movement, that will be negative. So I can write minus P times A, and this force and multiply by perpendicular distance A will also produce a moment counterclockwise. So it will be positive PA. So it means that moment about Z is equal to 0. Similarly, if you take moment about X axis, so you can see that this force into perpendicular distance A is producing clockwise movement, and this force which is having perpendicular distance A is producing counterclockwise movement. So their sum will also give you net movement about X axis will be equal to 0. So now in this condition we have if you want to move this all forces to the centric load, so force will be equal to 4 times P, and there will be moment about X is equal to moment about Y will be equal to 0. So only in that condition we have centric axial load, which is stress, and that stress will be equal to minus F by A, because all these forces are compressive. So if you put F, so minus 4 times P divided by area is pi A square. So what we will get is that we will get normal axial stress will be equal to minus 4P divided by pi A square. Okay, now we'll move toward our main problem. That is, first portion is that when the force at D is removed. So I will write it force at D is removed. So when you remove this force, let me, if I cross this force If I remove this force, so we have only 3 force. So in this condition, we can write here F will be equal to 3 times P, and you can see you will have moment about x-axis as well as moment about y-axis. So we sorry, z-axis, not x y-axis. It is moment about z-axis and about z. Now we will see what will be the value of this. So you can see this is moment about z. So this force is producing clockwise movement and this force is producing counterclockwise movement about z. They both will cancel. So moment about z will be equal to 0, and this is your x-axis. So only this force, which is P multiplied by perpendicular distance A, is producing clockwise movement, so it will be negative. As this force is removed, so only there is a negative movement, and that will be equal to minus P times A. Now you can see that due to this normal force, we will have stress, which is equal to minus 3P divided by A, which is equal to pi A square, and due to this movement of x, we have bending stress. So this is normal stress, clear, and we will have bending stress, which is also contribute towards normal stress, and that bending stress we can write it as mx into z divided by I double x or I. So you can see you have mx is minus pa. Now what is z? So z, you can see z is distance from the central or from this neutral axis to the point where load is applied, and it is opposite toward this a, clear, and that we can write it as minus a. So minus pa into minus a divided by pi by 4 a power 4. Okay, so when you solve this, it will give you pa square over pi by 4 a power 4. Okay, and when you simplify it, will be equal to 4 times p divided by pi a square. Now total stress will be equal to normal stress, normal, plus the stress due to bending. And we can write it as that this will be equal to minus p by minus 3p over pi by a square minus this 4p by pi a square. Now what is the reason that we have put a minus sign over here? So I will show you. You can see this is the force and this is perpendicular distance, and it is producing clockwise movement. So about this axis, this portion will be in compression while this layer will be in tension. It will be bent like this, clear? So here there will be compression. So that is why we have taken it as negative. So when you add them, it will give you minus 7 p over pi a square. That will be the total maximum normal stress when d is removed. So I can write it maximum stress is equal to minus 7 p over pi a square. And this is the answer of our first part. Now in second part, we have been force at C and D is removed. So when you removed the force at C and D, so I will remove this force as well. So you can see now we have total 2P are acting on that. So force will be equal to 2P, and we will have moment about X as well as moment about Z. We will see what is the moment about x-axis. So this is your x-axis. So moment about x-axis is this force into perpendicular disc. It is producing clockwise movement, so it will be taken as negative. So it will be minus PA. And similarly, moment about z-axis is also P into perpendicular distance A, and it is producing clockwise, so it will be minus PA. So I will write it. Mx will be equal to minus PA and mz is also minus p into a. Now total maximum stress will be equal to what? It will be equal to minus F by A, because that is compressive, minus M into C divided by I, where M is the total moment, C is the distance from neutral axis to the point where loads are applied, and I is the moment of inertia. You can see that this moment is about x-axis and this moment is about z-axis. So what we will do, we will get resultant bending couple, and that resulting bending couple, by using Pythagoras theorem, it will be equal to m into m is equal to mx square plus mz square. So put the value minus pa whole square plus minus pa whole square under the root. That will give you resultant moment. So it will be equal to p square a square plus p square a square under the root, and we can get it 2 times p square a square under the root. So if you take it out, so we will get under root 2 times p multiplied by a. So you have all the value, just plug it in here. So f is minus 2 times p divided by pi a square, and there is a minus because it will create compression at the point where this load at B is applied. So we will take this minus. So minus under root 2 PA, and what is C? C is also P, because C is distance from this neutral axis till the point where this load is applied, one of the load which is at a distance A. So I will write it A divided by I is pi by 4, A power 4. Okay. So when you solve this, you will get maximum bending stress, and that maximum bending stress will come out to be minus 2.437 P divided by A square. And this is the answer of the stress for the load when it is removed from C and D. Now what about the numerical values? Since we are given that P is equal to 100 kilonewton and A is equal to 40 millimeter, that is equal to 0.040 meter. So just plug it in this formula. So if I will put it, minus 7 times multiplied by P is 100 kilonewton. So 100 into 10 raised to power 3 divided by pi, and area A is 0.04 square. Clear? So after solving this, you will get the value will be equal to minus 139.3 into 10 raised to power 6 Pascal. Or you can see that maximum stress is equal to minus 139.3 megapascal. So this is the numerical value or answer of our first part. And in second part, if you put it the value, so minus 2.437 multiplied by 100 into 10 raised to power 3 divided by 0.04 square. So when you solve this, you will get maximum normal stress will be equal to minus 152.3 into 10 raised to power 6 Pascal, or you can say that maximum normal stress is equal to minus 152.3 megapascal, and which is the answer of our second part when force at point C and D are removed. So this was all about this problem 4.107. I hope you have enjoyed this video and you have learned from it. Those who are new to my channel, then subscribe it and don't forget to press the bell icon so that you can get notification about my latest videos. If you have any question, you can ask me in comment section. Thank you for watching.